Okay, in this video, which I will probably end up splitting into multiple videos because there is a lot of material in this last chapter, we will talk about the particle zoo, which is the last chapter of Unit 4. So let's write down the title. So the particle zoo. Okay, so in this chapter, we will talk about particle physics pretty much, the energies associated with particles, and the interactions and forces experienced by particles and stuff like that. So this is a chapter on modern physics pretty much for those of you who are going to go beyond the A-level physics and study physics at the university. So let's start by mentioning Einstein's theory of relativity. Okay, showed that energy and mass are equivalent. This means that if we have some form of energy, we can turn that energy into mass and vice versa. Okay, an amount of mass, any amount of mass carries some energy. Okay, and I'm gonna try to proceed fast. This boils down actually, to the most famous equation in physics pretty much. So E is mc squared, or delta E is delta m c squared. This tells you that, let's use green, so if we have some mass, okay, an electron, say, which is the example I'm going to talk about. If we have an electron with mass, the mass of the electron is 9 times 10 to the negative 31 kilograms. That mass of the electron by itself carries some energy. And because of this factor here, c squared, and I remind you that c is 3 times 10 to the 8 meters per second. And if we square that, we get 9 times 10 to the 16, right? So that's a huge amount of energy carried by mass. Okay, how much? Let's go see. Let's go do an example. The mass of the electron, I said 9, but it's actually 9.1 times 10 to the negative 31 kilograms. Okay, so using E equals to mc squared, we immediately see that we have 9.1 times 10 to the negative 31. Okay, I'm gonna carry the units to the right, and then we have c squared. Always use parentheses with these kinds of calculations, guys, because it's really easy to mess up. So, and forget to take the square of c, okay, so 3 times 10 to the 8 squared, and we have meter squared per second squared. Okay, so if we make this calculation, we find 8.91 times 10 to the negative 14 joules. And then what is kilograms times meter squared over second squared? That's the same as 1/2 mv squared, right? So we have mass times velocity squared, so that's joule. Okay, so that's joules. And I forgot to mention this, but energy, since this is energy, mc squared evaluates to joules. So recall another unit of energy we talked about in previous videos is the electron volt. So recall that 1 electron volt is 1.6 times 10 to the negative 19 joules. So if we combine that, we find that the energy carried by 1 electron is 511.9 kilo electron volts. Now, the next thing I'm going to talk about is about 2 examples where we see this conversion over here of energy into mass and mass into energy takes place. Okay, so the best examples are pair annihilation and pair production. So let's start by talking about pair annihilation. Okay. So pair annihilation is the phenomenon in which 2 particles with opposite charges, so that's the particle and its corresponding antiparticle, that's something we are going to talk about next, interact and 2 photons are produced. So two particles with opposite charge and opposite quantum numbers. Keep this thought, we're going to come back to this later. And opposite quantum numbers annihilate into 2 photons. Okay, so we're going to talk about why we need 2 photons in a moment, but if we have an electron and a positron interacting, the positron is the anti-electron. It's an electron with positive charge. Okay, 2 photons are produced. And similarly, if we have a proton meeting its corresponding antiparticle, which is called the antiproton, again 2 photons are produced. Why do we need 2 photons? For momentum conservation. Okay, and let's go see that. Let's say that we have an electron with some momentum p traveling to the right, and a positron with momentum minus p, and the minus sign corresponds to the opposite direction. Okay, these 2 guys interact head to head, meaning that the total momentum before is 0. Therefore, if we only had 1 photon coming out, okay, then nothing will cancel its momentum, right? So we need another photon in the opposite direction to cancel the momentum of the first photon, okay? Because if 1 photon was produced, we will have a violation of the conservation of momentum, okay? So that's pretty much it. The next thing that I promised to talk about is pair production, okay? What is that? It's the opposite. We have a photon turning into 2 particles, okay? So an energetic photon interacts with a nucleus to produce a particle and the corresponding antiparticle. Okay, so since I used red for the photons earlier, I'm going to use red now. So let's say we have a photon, and let's suppose that this is a nucleus. Open circles mean, let's say, neutrons, and closed circles means protons. So the photon interacts, and we have a positron and an electron coming out, okay? So why do we need the nucleus? For momentum conservation again. So I'm going to put this as a note here. Note, the nucleus, which is sometimes called the recoil nucleus, is needed for momentum conservation. Let's now talk about the energies involved in this reaction. So let's talk about the energies involved. Okay, we already saw earlier that, for example, 1 electron corresponds to an energy of 511 keVs. So the mass of the electron, if it's converted to energy, we get 511 keVs. So if we have a positron and an electron coming in, and if we have 2 photons produced, let's go see what the frequency of those photons should be. So in special relativity, when relativistic masses are involved, and when we deal with particle interactions, we don't have the conservation of energy, but we have the conservation of mass energy. This is how it's called. So we need to have mass energy before must be equal to mass energy after. Okay, let's go see what I mean by that. So how much energy do I have before? Since mass corresponds to energy, I have the mass of one electron times c squared plus the mass of the positron, which is the same as the mass of the electron, times c squared. So this is the rest mass, as it's called, because that's the energy a body has when it's not moving. What other energies are involved? Plus 2 times the kinetic energy of these two particles, right? So 1/2 mv squared. We can use this. I'm gonna put a note here. Note 1/2 mv squared only works if the velocity is much, much smaller than the speed of light, or velocities smaller than or equal to about 0.05 c, so 5% the speed of light. Okay, so we can use 1/2 mv squared in those cases. I'm going to talk about what we use in relativity later. So let's go back to this equation. And I forgot to say what's the mass energy after. So before we have in this reaction still, okay, so we have this energy, this mass energy before, and let me erase this, and this should equal 2 times the energy of the photons, okay, because we have 2 photons, we have 2 times the energy of the photon. Okay, now let's do one simplification here. So assume that V is 0. Okay, therefore the equation simplifies to 2 times the mass of one electron times c squared equals to 2 times, what's the energy of one photon? It's h, Planck's constant, times the frequency, right? So the frequency, these two cancels, so the frequency is equal to, the frequency of the photons produced is equal to the mass of the electron times c squared over the Planck's constant, right? So if we plug in numbers, we find 9.11 times 10 to the negative 31. Let's put the numbers to the left and the units to the right, as we have been doing in all these videos, if I don't forget my units. So mass is in kilograms, then we have times c squared. Always use parentheses when you take when you calculate c squared. So 3 times 10 to the 8 squared, because I've seen many students only putting the speed of light once, so you need it twice. You need to square it. Okay, what are the units for speed? Meters per second. If we square them, we get meters squared over second squared. And in the denominator, we have Planck's constant, which is 6.63 times 10 to the negative 34. The units are kilograms meters squared over seconds. So kilograms meters squared over seconds. Okay, so that's Planck's units. So this second with this second cancels, kilograms cancel, meters squared cancel, and if we do this calculation, we find 1.24 times 10 to the negative, times 10 to the 20 hertz. That's a really high frequency. Okay, let's go find the wavelength of this thing. So since c is lambda times f, then lambda is c over f, and if we plug in numbers, we find 2.43 times 10 to the negative 12 meters. Okay, let's go find the minimum wavelength for pair production. Okay, so in pair production, so minimum lambda for pair production. So in pair production, we have a gamma plus nucleus producing a positron and an electron. Okay, so what is the energy? So mass energy before should be equal to the mass energy after, okay? And for a moment, we will pretend that the nucleus does not exist in this equation, okay? So it doesn't play a role. So we will have that the mass energy before is h times the frequency of the photon, and after we have 2 times the rest mass of one electron, assuming that the pair production produces an electron and a positron at rest, okay? So hc over lambda is equal to 2 times the mass of the electron times c squared. So lambda should be equal to h times c cancels, okay? So lambda should be h over 2 times the mass of the electron times c. So we have 6.63 times 10 to the negative 34 joules times seconds, which are the units for Planck's constant, joules seconds. And we have 2 times 9.1 times 10 to the negative 31 times 3 times 10 to the 8. Actually, let me bring this down here, okay? And we have kilograms, meters, seconds. So this all boils down to lambda equals to 1.21 times 10 to the negative 12 meters. So 1.21 picometers. So lambda equal to 1.21 picometers is the minimum wavelength of a photon capable of producing an electron an electron positron pair, okay? And I will stop the video here, and in the next one I'm going to talk briefly about special relativity before moving on to other things.